The Karakum Desert stretches across Turkmenistan as an unbroken expanse of arid, flat terrain. Beneath this rigid surface lies a vast network of shallow natural gas reserves. In 1971, a Soviet geological team arrived to exploit them. The engineers positioned a heavy exploratory drill rig directly over what they believed was a standard subterranean gas pocket. Subsurface gas is held in place by a layer of impermeable stone known as the caprock. As the drill bit penetrated this barrier, it compromised its structural integrity. This created an immediate pressure imbalance. The sudden venting of pressurized gas meant there was no longer enough internal pore pressure to support the immense lithostatic weight of the rock above it. Without that underlying support, the mechanical strength of the earth gave way. The entire drill rig plunged into a newly formed sinkhole. The Darvaza crater resulted from the predictable mechanics of subsidence, the physical collapse of a roof that could no longer sustain its own weight. The collapse was only the immediate physical consequence. The exposed crater was now uncontrollably venting explosive methane and highly toxic hydrogen sulfide directly into the atmosphere. Left unchecked, this invisible cloud posed a lethal, immediate threat to both the drilling crew and the surrounding desert ecosystem. To neutralize the threat, the engineers turned to a standard petroleum engineering protocol, controlled flaring. Flaring uses combustion to convert toxic, unrefined emissions into less harmful byproducts before they disperse. The Soviet team intentionally ignited the crater, estimating that the localized leak would burn itself out completely within a matter of weeks. That was in 1971. The crater has been burning continuously ever since. This breaks the expectations of standard hazard mitigation. To understand why a temporary protocol resulted in a permanent flame, we have to look at what the engineers misjudged about the earth beneath them. The decision to ignite the gas was rooted in strict mathematical logic. It relied on a specific assumption, that the drill had punctured a discrete and isolated pocket of gas. This schematic shows their intended model. They envisioned a finite boundary around the trapped methane. If you know the volume of that box and the rate of combustion at the surface, you can map the timeline to zero fuel. In a closed system, this follows a standard depletion curve. As the gas burns, the internal pressure drops predictably until the fuel is exhausted. Yet Darvaza's output shows no signs of following a depletion curve. The pressure and volume have not diminished. The reality is that the Karakum Basin sits atop one of the most massive, continuous natural gas reserves on the planet. The drill bit tapped into a localized node that was connected to a vast regional network. The flaring protocol failed because of a volumetric miscalculation, a bounding box fallacy that ignored the true scale of the reservoir. To see how this network functions, this cross-sectional map reveals the deep strata beneath the desert floor, extending miles out from the crater. These deep sandstone layers possess high porosity. They are riddled with microscopic empty spaces holding pressurized methane. They also possess high permeability, meaning those individual pores are interconnected, allowing gas to migrate freely through the stone. When the crater ceiling collapsed, it created a permanent void, violently altering the pressure gradient of the entire region. The open crater acts as a massive exhaust vent. The localized pressure at the surface is now drastically lower than the surrounding subterranean rock. In physics, the movement of fluids and gases through porous media is governed by Darcy's law. According to Darcy's equation, the highly pressurized gas miles away from the crater is forced to migrate through the permeable rock toward the path of least resistance, the new low-pressure zone at the surface. This creates a subterranean recharge network, pulling fuel from an area vastly larger than the original drill site. The crater serves as a geologically driven vacuum, actively stifling methane from the surrounding crust through high permeability strata. We can actually see the endpoint of this migration network right at the surface. If you look closely at the crater walls, you'll see hundreds of individual pockets of flame. These separate fires burn at the terminal exhaust points of the permeable rock, serving as continuous feed lines from the deep reservoir. This brings us to a state of thermodynamic equilibrium. The rate at which the subterranean methane flows through the rock and recharges the crater perfectly matches the rate at which surface oxygen allows it to combust. Because these forces are balanced, the fire pulls enough fuel to avoid burning out, but is physically constrained by available oxygen, preventing it from growing larger. The longevity of the flame requires no supernatural explanation. It is a fluid dynamics equation solving itself continuously in real time. The engineers in 1971 calculated a localized chemical reaction while ignoring a regional geological system. When localized interventions ignore the macroscopic rules of fluid dynamics, standard mitigation protocols break down. The attempt at a temporary controlled chemical conversion instead created a permanent atmospheric bridge for the deep gas reserves. The crater functions today as an unpluggable permanent atmospheric vent for a massive regional gas reservoir. The sheer physical scale of the continuous combustion has now completely integrated itself into the surrounding desert ecosystem. It has transitioned from a temporary engineering error into a permanent scar on the lithosphere, a dark geographical landmark. Underestimating the subterranean permeability of the Karakum Basin transformed a localized hazard into a permanent, self-sustaining geological fire.